Hi, it's Cameron Gibelyou again, and this time I'm talking about the life of our sun and stars like the sun. If you're taking big history, this talk will help you understand the units on how the solar system and Earth formed. The sun might seem permanent. After all, it's there, up in the sky, day after day. But the sun too has a history. It was born some 4.5 billion years ago, and it will die someday. Stars are born in immense clouds of gas and dust that exist within galaxies, such as the star-forming regions shown here. The story of star formation is a story of a battle between pressure and gravity. Whether we're talking about the sun forming 4.5 billion years ago, stars forming in galaxies around the universe today, or the first stars forming in the distant past. Gravity draws matter together and so tends to make gas clouds collapse. But any cloud of gas exerts pressure, just like the gas inside a balloon exerts pressure on the sides of the balloon. In the case of a gas cloud in space, the pressure from the gas, as well as the influence of magnetic fields within the cloud, tend to prevent the cloud from collapsing under its own gravity. Still, while gas clouds often stay stable for long periods of time, a number of processes can cause parts of a cloud to collapse under their own gravity, and once a cloud starts collapsing, it tends to keep collapsing. The cloud may fragment into several smaller clouds, which then continue collapsing individually, and the central regions of these smaller clouds become denser as more matter falls into them. Eventually, though, as density and temperature increase at the core of a collapsing cloud, pressure too increases, and pressure halts the star's further collapse. The object is now called a protostar. Material continues falling into the protostar, increasing its mass. Instead of falling directly onto the protostar from all directions, the surrounding material typically forms a rotating disk called an accretion disk that swirls around and gradually into the protostar, as shown in this artist's conception of the process. Why does a rotating disk form? The matter rotates around the protostar because matter in a collapsing gas cloud always has at least a little bit of overall rotation to start out with, due to the random motions of matter within the cloud. And as it collapses and becomes smaller, it spins faster, just like an ice skater spins faster when she collapses by pulling her arms in. And spinning matter naturally forms disks. Just like pizza dough when you spin it into the air, a spinning gas cloud naturally settles into a disk. If the star is to have planets, they must form in this disk before the material falls into the star, or gets swept away from it by light and particles coming from the star. Fortunately for us, that's exactly what happened in the disk that surrounded the young sun. The fact that the planets formed in a rotating disk of matter is, we think, why most of the planets both revolve around the sun and rotate around their own axes, in the same direction that the sun itself rotates. The process of gas cloud collapse and star formation typically takes millions of years to happen, so we can't watch it unfold in real time. But astronomers have captured some incredible images of stars at different stages of forming, including protostars with disks around them that may develop into planets. So we can actually see the birth of stars unfolding in other parts of the Milky Way, and learn something about our own sun's past by observing. When the density and temperature of the protostar's core rise high enough for nuclear fusion to begin, a star has officially been born. The amount of mass that a star is born with determines both its volume and its brightness, as well as its lifespan. Star masses can range from anywhere around 1/10 of our sun's mass, up to more than 100 times our sun's mass. All stars spend most of their lives on the main sequence of the Hertzsprung-Russell diagram, fusing hydrogen into helium in their cores. A star with the mass of our sun lives for about 10 billion years, and since the sun was born about 4.5 billion years ago, it is currently about halfway through its lifespan. Striking changes will occur to the sun something like 5 billion years from now, when the hydrogen in its core finally runs out. We can apply what we know about how stars age to predict the sequence of events. Without any hydrogen in its core, the Sun will start fusing hydrogen in a layer or shell outside its core. The large amount of energy produced by this fusion will drive the outer layers of the Sun outward, and the Sun will expand to over 100 times its current radius, becoming over 1,000 times brighter than it is today. This process won't happen overnight. It will take something around 1 billion years. But the result will be that the Sun will be a red giant, and Earth, if it does not fall into the Sun, will orbit next door to the surface of the Sun. Either way, our planet won't be such a friendly environment for life when those days arrive. It will be an unimaginably hot inferno. As the Sun's outer layers expand, its inner layers will actually be collapsing, because without fusion at the center of the star, much of the pressure is gone that held the core up against collapse. As the core collapses, it becomes hotter, until eventually it's so hot that fusion in the core can start again. But this time, it's helium that undergoes fusion, making carbon and oxygen. When helium fusion begins, the Sun will again shrink in size and luminosity, and although it will still be bigger and more luminous than it is today, it will be nowhere near as large as it was as a red giant. It will only stay this way for around 100 million years though, and then the helium in its core will run out. Hydrogen and helium fusion will continue in shells around the core, and the energy from this will again drive the outer layers of the Sun outward, causing it to increase in both size and luminosity, and it will once again be a red giant. But this stage 2 will last a mere tens of millions of years, and eventually the Sun's outer layers will separate from the star entirely, leaving only the mostly carbon and oxygen core to shine as a white dwarf. As the white dwarf near the center of this image shines on its own ejected outer layers. Those outer layers will soon merge with the surrounding gas and dust and disappear from view, and the white dwarf that was our Sun will gradually radiate away its energy, cooling down until it stops shining altogether after trillions of years. The planets, if any remain, having avoided the fate of being swallowed by the Sun or ejected from the solar system by the gravity of a passing star, will be dead, dark worlds revolving around the fading ember we used to know as the star that gave us life. So the next time you look up in the sky and see the Sun, remember, it may seem like the most permanent and reliable thing in the world, rising faithfully every morning and setting faithfully every evening. And that's certainly going to be true for the rest of our lifetimes, and billions of years beyond. But it won't be true forever.